Hi, my name is Grace Lamb. This is my Physics 2211 Lab 5, the falling slinky. Okay, so starting off with an introduction to this lab, the purpose of this lab is to observe the motion of a stretched slinky drop from static equilibrium with the goal of determining whether or not the bottom of the slinky in the computational model stays stationary. And in order to accomplish this goal, a video will be analyzed using tracker, allowing for the observed motion to be calculated and all the initial conditions to be found. Then, using the fundamental principles in Newton's second law, the momentum principle, gravitational force, and drag force, a glow script code will be manipulated in order to create a computational model of all of the observed motion. A brief preview of the results of this lab is at the bottom of the slinky of the computational model does stay stationary as it does in the observed motion as well. And the assumptions for this lab is that the only force acting on the system are drag and gravitational with no other forces present. And the system is going to be the slinky and the man, and the surroundings is going to be everything else, including the earth, the air, and everything else. As mentioned before, the fundamental principles for this lab is Newton's second law, which means force equals mass times acceleration, the gravitational force, which is Fg equals mg, and then the drag force, which is Ft equals b v squared, and b is just going to be a constant that allows the drag force to work. And then the momentum principle, and from this we're able to derive a velocity update formula and position update formula that we're going to use in the glow script code. And then how I was able to do this is I imported a video into Tracker, and then I analyzed the Tracker data to determine the initial conditions. Then I created a glow script code to reflect the observed motion using the initial conditions and the fundamental principles that I just shared. And then I was able to compare the computational model with the observed model to see if the bottom of the slinky is stationary. So for the observed motion, I used a video that was included in the assignment, and I put this into Tracker, and the first thing I did was calibrate it so that as the height of the man was given and so was the mass of the ball, so those are two initial conditions. And once I did that, I used point mass on Tracker in order to track the entire thing, which allowed me to get the initial condition and then also the initial velocity. In this case, initial velocity is going to be 0. And then once I found these initial conditions, I began creating my glow script code. So I put in the mass of the ball as well as the position, initial position vector, and the initial velocity vector that were given from the Tracker data. And then I also set the delta t to the time change that Tracker used. And then I put in the constants of g, which is known, and then b, which you just derive and see what works best. And then I put in the unit vector for the y direction, as the y direction is the only direction that is going to be used in the computational model. And then once all the initial conditions were created, I was able to make a loop that mimicked the stationary at the when the bottom is stationary at the very beginning of the video. So I used Fg, and I put in that, and then I put in Ft. So in this case, Fnet is going to be equal to 0. So there's going to be no change in the bottom in the y direction. So it makes it so that the position does not change at all, which is why the position is going to be stationary in this part. So that's shown as Fnet is going to be equal to Fg plus Ft. In this case, Ft and Fg are the same, so they'll end up canceling out. And I created another loop to show after the slinky falls from that stationary position. And in this case, Fg and Ft are not equal to each other, so Fnet is not equal to 0, so there is going to be a change in displacement of the y. So I did that by setting Fg like I did originally, and then I put in the force of drag, and this allows the position of the y to change, and I used the position update formula and the velocity update formula to put this in there. And once all my code was done, I was able to run my code, and this is the position versus time graph of the y direction that glow script ended up outputting, and then I compared this to the results of the observed motion. And then once I compared the observed and predicted motion, as you can see, they are extremely similar, which means that the computational model was able to accurately predict what the observed motion showed. However, you can also see that there are slight differences in between the Tracker data, which is going to be the blue, and the glow script data, which is going to be the red. And the possible sources of error in this case, the first one is that glow script doesn't consider the human error in collecting the data on Tracker, so that may have caused this variation. And secondly, there may have been other forces acting on the system besides the force of gravity and drag in the observed motion, and the predicted motion does not take into account that. But overall, the glow script model was able to accurately predict the Tracker data and was able to show that it stays stationary for a significant period of time until drag is introduced to the equation. So for the questions that I created, the what does this mean question, why does the bottom of the slinky stay stationary for a period of time? As I mentioned earlier, during that time, Fg equals Ft, so all the forces in the y direction are balanced and they cancel out, allowing there to be no position in the no change in position during this time period. And once the slinky fully compresses to like at the stationary point, the y direction forces are no longer balanced, which is why towards the end you can see that it's obviously changing positions in the y direction. And then for my what if question, if the slinky was not fully stretched out, would it have the same result? And yes, the experiment would yield the same result, as the y forces will still like cancel each other out, allowing for the bottom of the slinky to be stationary for a period of time. However, just because that stretch would be smaller, the period of time that it's going to be stationary is also going to be smaller. So thus changing the length of the string or the length of the stretch of the slinky won't change this, like if it's going to be stationary at the bottom, rather there's the time and distance it is that way. And thank you guys so much for listening.